Moving on to 6.2, we talk about circles and angles, and a lot of this is just going to continue our geometry review from what I would call your prior knowledge. So let's start with a circle, because a lot of what we talk about in trig once we get past triangles deals a lot with circles. Here are some of the parts of a circle that you might have learned already. First, we have an arc. So here is an arc, and an arc is just a segment of the circumference of a circle. We have two types of arcs. We have a minor arc, so this is the one that I just wrote in. So if we have points A and B, for example, the minor arc is the shorter distance from A to B, and the major arc is the longer distance from A to B. Most of the times we're going to assume that we're talking about the minor arc unless I tell you otherwise. A chord joins any 2 points on the circumference. So here's A and B, right? These are 2 points on my circumference. So this line segment here, AB, would be a chord. And then we have a secant, and a secant is just a straight line that intersects the circumference. So here is my secant. And then of course we know that this is a radius when the segment comes from what we call the center. So this would be the center, this point in the middle. Sometimes we call that center O. And then of course we have our diameter, which is just a specific type of chord, I suppose, right? Because it still joins 2 points on the circumference, but those points are opposite each other. So chord and secant might be new, but hopefully arc, radius, diameter, those are or should be review. Well, we continue with our circles when we talk about measuring angles, and we talk about radians. And we define a radian using a circle. So a radian is defined as the angle required to produce an arc equal in length to the radius. So angle required to produce an arc equal in length to the radius. So the way this kind of came about is the Greeks, I'm assuming, with nothing better to do back in the day, instead of talking about what we know as degrees, decided to come up with an angle measure that related the angle to the circle itself, and this is where we got radians from. And because of this definition, that we're kind of equating it to the radius, what you really need to know here is that there are 2 pi radians in a full circle. That's the important piece here. That's the key. And we also know that there are 360 degrees in a circle, so it establishes this conversion rate that is really important in trig, which is that 2 pi radians, sometimes you'll just see rad, is equal to 360 degrees. And this is a conversion ratio that we can use just like any other conversion ratio if we were to convert between feet and inches, or kilometers and miles, radians and degrees. So let's practice really briefly here. If I want to convert from degrees to radians, so I'm given 60 degrees, and I want to know how many radians that is. Well, think about your unit conversions, especially if we think back to like if you took chem and did unit conversions in chem. We want the unit we're trying to cancel opposite each other in the fraction. So if I'm going to set up my conversion ratio here, 60 degrees, I want 360 degrees in the denominator and 2 pi radians in the numerator. Right, that's going to allow my degrees to cancel out, and that leaves me with, well, 120 pi over 360 radians, which we should probably reduce to get to pi over 3 radians. So here's, actually, this is going to be an important conversion later, is that 60 degrees is equal to pi over 3. Likewise, we can go the other way. Because radians are a ratio from the circumference to the radius, right, and those are both units or measurements of length, Radians are considered a unitless measure. So if you see a number like 5 pi over 6 and there's just nothing there, we can assume that we're talking about radians because of that, quote, unitless measurement. So I want to convert from radians to degrees now. Just like we did before, I want to make sure my units are opposite each other. When I think units, even though it's a unitless measure, when I think units for radians, I think pi. So I want to make sure my pi in the radian measure and the pi in my conversion ratio are opposite each other. So I have 360 in the numerator. So my pi's cancel out and I get whatever the heck 360 times 5 is. I get 1800 over 12, which is 150 degrees. So 5 pi over 6 and with 150 degrees. This conversion ratio is crucial. You will occasionally have to convert between radians and degrees, and you should be prepared to do that. You should know how to do that. The last bit I want to talk about with circles is sectors and segments. So sectors are regions bound by 2 radii and an arc. Regions bound by 2 radii, which is just the plural of radius, because radiuses is kind of clunky. So we have radii and an arc. So this region right here is a sector. This is my sector. A segment is similar, and it's the region bound by a chord and an arc. A chord and an arc. So this region right here is a segment. So sectors and segments, just so we're familiar. The other thing we talk about when we start to introduce sectors and segments is to talk about the length of an arc and the area of a sector. When we talk about arc length, we're talking about, remember we said that arcs are parts of a circumference, right? Part of the circumference. Circumference. So when we want to find the length of an arc, we can actually adapt the circumference formula. I should have switched colors here. So we actually, this color, can adapt the circumference formula. And the way we're going to adapt that circumference formula, well, we know that the circumference of a circle is 2 pi r. Well, the length is just a proportion of the full circle. So the arc length is theta over 2 pi, right? It's whatever this proportion of the entire circle is. But we can also simplify this because why deal with that formula? It's just pi times r. So the arc length is just pi times r. But I like to show you where it comes from because sometimes that'll help people think through it. The key here is that that theta, did I say pi r before? I should have said theta r before. I'm sorry about that. Just theta times r. And theta has to be in radians. The thought process behind sector area is actually very similar. Remember that, well, a sector area, well, this is just kind of a piece of the pie, right? This is just part of the area. Part of the area. So under the same logic, we can just adapt our area formula. Right? We know that the area of a circle normally is 2 pi r. Well, no, it's not. It's pi r squared. I was writing it right, but I said it wrong. It's pi r squared. And again, we want a proportion of that whole circle, right? We want a piece of the pie. We want just this part, not the entire 2 pi radians. So we want to apply that same kind of proportion idea, theta over 2 pi, and we can reduce this again. We can try to simplify this again for us, and we wind up getting 1/2 theta r squared. Or I prefer to write it as r squared theta, but it all means the same thing. And again, theta needs to be in radians, so these only work when theta is in radians, and that's kind of part of the reason why we have radians, is because of this relation here, right? Because radians are based on the circle and based on the circumference of the circle, we're allowed to do this and work with radians. If you're given something in degrees, just convert it to radians first when you have to do something like this. Let's try an example. An angle of pi over 4, again that's implied to be radians because there's no unit given, sweeps through a circle of radius 3.5 centimeters, and I want to find the arc length and the sector area. Sure, so here is my circle, here's my radius, and my angle is pi over 4. So here is my pi over 4, and I want to find the length of this sector, and I also want to find the area, the length of the segment, and I also want to find the area of the entire sector. Not a problem, right? We have the two formulas, and they're fairly straightforward formulas. So the arc length is just given by the radius times theta, as long as that theta is in radians. And sometimes you'll see me write RAD in subscript, just so I remember that it has to be in radians. All right, well, it's just 3.5 times pi over 4, and that's going to be 3.5 times pi, 3.5 times pi over 4, and I get approximately 2.75 centimeters. 3 significant figures because I'm rounding, and that's the IB way. Likewise with sector area, 1/2 r squared theta, and again theta in radians. 1/2, 3.5 squared, times pi over 4, pi over 4, and I get approximately 4.81 centimeters squared because it's area now, so I have to have a squared unit. And that's all it is. It's just the two formulas for arc length and sector area. We can do some more interesting things with these, but at its core, that's what it is, kind of just introducing the formula to you.